Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is going to look at the mathematics and the statistics of the dice game of craps. And so this is, I like to use this example for many of my classes because it shows randomness of values in computer science, it shows statistics, it shows mathematics, it shows a little bit more than a lot of the other examples. So the game of craps, if you've ever seen, you can look at it right here, it looks so darn complicated. It looks intimidating. And the first time I ever went to a casino, it was very intimidating. There's a lot of people and there's a lot of excitement. They all know what's going on and you're just walking into this not having a clue what's happening. But very quickly, you can figure out what's going on. So the game itself we're going to show here is quite simple. And you could see everything that you see here, all the flash and show on the board, is basically just keeping track of everyone's bets and letting you know where your money is on the table, so there's no fancy business of, where did my bet go and things like that. So, but let's just talk everything else out here, and we can discuss the easiest way to play the game, because you could tell there's many, many different bets here. But we're going to talk out the game and discuss how the pass line odds are calculated. And so this is kind of how, like I said, there's a lot of bets here. There's pass line, don't pass. There's come, don't come. Over here, there is, you can play the numbers, you can play other different types of bets, you can play a field bet, but again, we're just to get you, just to get you, just to get you in that chair or get you to stand up and play the first part of the game. Let's talk about the pass line bet. Oops, and so the game itself, let's just talk about, we're talking all the mathematics, so let's just get down to it. You're throwing two six-sided dice. Normal, there's 1, 2, 3, 4, 5, and 6. They are, just a normal die. Each die result is an independent event because you're throwing two separate dice. They're not connected to one another in any way. And so since there are 6 possible results per die and they're independent events, you have 36 possible results per throw of the two dice. And saying a 2 and a 1 versus a 1 and 2, even though they get you to the same spot, that's a 3, those are actually very different things when it comes to the possibility of throwing the dice. And so you'll see here when we go through things that the probabilities of some numbers are greater than others. And that's just the way that that's the way the dice roll. So a result value of 7 is always going to be the most probable. And again, we're going to show all the math here. And a result value of 2 or 12 are going to be the least probable. And so I just wanted to put this out here in C++, that just to show you that I see this, the incorrect way to simulate this in C++, I see this quite often because the rand function will give me a value from 0 up to the number -1. So for down here, the incorrect thing, like you'll get the right range, I'll always get a value between 2 and 12 because 2 is the smallest number and 12 is the largest, because this rand function will give me something between 0 and 10, inclusive on both ends. And so I'll get 2 to 12. I'll get the correct range, but using this, everything is equal odds. There's an equal chance of it's like spinning a wheel versus rolling dice. Spinning a wheel where everything has the equal possibility of being called. And so this is half correct or a third correct or what, I don't even, I'm not going to go down to how correct that is, but that's not 100% correct. So this up here, this is the way you would go about doing things. Start with 2 and then give me a number between 0 and 5 inclusive. Give me a number between 0 and 5 inclusive. Add the 3 numbers up, and that gives me the correct way to go through and figure out the result of my roll. Okay, so we're going to be covering the pass line bet here and just the mathematics. I'm not writing any code. That was the only code you'll see in the previous slide there. And so the game itself is rather simple. There's you start a game, you go, okay, we're starting a brand new game of craps here. And so you roll the dice. And if I roll a 7, I win. If I roll an 11, I win. If I roll a 2, I lose. If I roll a 3, I lose. And if I roll a 12, I lose. And so that sounds like a lot, but it's just the numbers in the middle and on the numbers on the end. 2 and 3 are on the low end, 11 and 12 are on the high end, 7 is right there in the middle. And it comes out to 1/3 of the time the game will end on the first roll. So it happens quite often. And so you go, okay, and then you start over again. The game's over. You either won or you lost. Your money's either doubled or your money's gone. But any other value, which is 4, 5, 6, 8, 9, and 10, those are the other numbers that are left that are possible out of our list, becomes what is known as the point. And this is where students have trouble, or just people have trouble. At this point now, whatever that number was, if I rolled a 6, that's the only number that matters. The 6 is the point. I just call it X because it could be any one of those 6 values. It's most probably going to be a 6 or an 8, but it could be any one of them because each one of those is possible based on our problem set. So let's call that value X, and now the game's rules change. And now all I care about is whatever that X value is, and I think I said 6, I already forgot, I'm just blabbing on about stuff. So either I care about a 6 or a 7. 7 is always going to be the loser, and the X, the point value, is always going to be the winner. Any other roll does not matter when it comes to this part of the game, this pass line bet. So if I roll a 12, doesn't matter. Roll an 11, doesn't matter. Roll a 2, doesn't matter. But if the point is X and I roll that again, if it's a 6 and I roll a 6, I win the game. And if the point is 6 and I roll a 5, nothing happens. It's not X. So we just keep on going until either I roll an X for a winner or a 7 for a loser. And nothing else matters at that point. It's not like you get every value in here. You get whatever you rolled on that first roll. And so you want to roll a 6 or an 8 because then you have the best probabilities of winning. A 4 and a 10, you have the smallest possibilities of winning. And that's all worked into the statistics of the game. And so we're gonna, this is what we're gonna work out. And my end goal is to show you, what percentage of the time will you win based on this rule set, and which percentage of the time will you lose, and is this a game you want to go to the casino and play? And I say hell yeah, but let's prove it statistically. Let's prove it mathematically. And we're not going to cover this in this video here, but the don't pass line is basically the exact opposite of the pass line. If you just go back between the two slides here, you can see basically I just switch losers and winners. And because it's basically the opposite. But the thing is, of course, if the statistics, the probability means that something is more than 50% probable, which is the house odds, they're not going to give you that. So the result of the don't pass, if I just switch the rules around, is they change the game just slightly so that you don't have the same odds that they have as the casino, because otherwise everyone would be playing on that side of the dice and the casino wouldn't be making any money. So just going back and forth between this, the don't pass line says 12 is a push, and a push is one of those things where the game just ends and no money changes hands. So if I roll a 12 on the first roll, just a push, and we just start over again as if nothing ever happened. So, and then the same rules go. Any other value that you roll becomes the point, and if I roll that number, this time I lose, and if I roll a 7, I'm a winner. And so, it's basically just playing the dice from the other side. You could play it from the player side or the house side, and it's up to you. You can play both when you're at the casino. And so that covers this part. So now let's discuss all the other parts. Let's do the statistics and the mathematics in Excel. Okay, so we go into a little more detail here. Here is a state diagram, and here is just basically all 36 results of the 2 dice that you can throw. So let me just say here, we're starting the game. Let me just re-explain this. You're starting the game here, and you roll the dice. You get a 7, you get an 11, you win. You get a 2, you get a 3, you get a 12, you lose. Any other number becomes the point. And so whatever number was rolled is now X. And so now you move into the secondary rules. If I roll that X value a second time, I win. If I roll a 7, I lose. And if I roll anything that isn't those 2, if it's not the point and it's not a 7, then I just keep on going, just keep on coming back, and the game ends. And these are the end points, right? This is just repeat, repeat, repeat. Theoretically, you could go on forever, but statistically, you will not. You will end the game in a few rolls because, basically 1/6 of the time you will throw the 7 and whatever else. So statistically, it'll end in 1 or 2 or 3 rolls. Sometimes it moves on. The more it rolls, the more people win. But that's something, again, that we don't necessarily care about. So this is the state diagram for something of what we just described in the previous slides. So now when it comes to all dice possibilities, again, since these are independent events, the 1, 2 and the 2, 1 are completely, we get the same result, the 3, but we get there from 2 different ways. And so they are completely different results when it comes to this. So this is all the 1s and all the 2s and all the 3s and all the 4s and 5s and 6s. And if I move to slide 2, you can see now these are the results: 2, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, 11s. I'm just summing up the 2 numbers that are inside each individual cell and mapping them into the new possibilities here. And so when I come to sheet 3, if I take all of this and I go, okay, there are 36 possible possibilities to this. And so you can see that the most probable is 7. There's always a way to roll 7 no matter what I roll on one die. But not everything else is possible. So there's only one possible way to roll a 2. There's 6 possible ways to roll a 7, and so forth and so on. So it's not a linear, it's not an equal possibility for everything. Every number has a distinct probability. So a 2 is rolled 1/36 or 2.78%. And so a 6 is rolled 1/6 of the time, 16.67%. So it's basically, almost like a curve. It's like a bell graph, but it's not quite a bell. It's more like a triangle graph, or forgive me for not knowing the mathematical term for it. So now with this understanding that these are the dice and these are the possibilities that can be rolled on in any one roll, now let's finally figure out the probabilities of winning this game and losing this. One quick thing to note is that the possibilities add up to 100%. So as we go and we take this from step to step to step, the possibilities and the probabilities of everything have to completely add up to 100% as we go. So if you screw up one way or another and your probabilities don't sum up to 100%, then you did something wrong, because you get less than 100% or more than 100%, then you haven't accounted, or you've counted too much for things that you weren't supposed to account for. So let's take a look again now. All right, so let's get into the nerdy math stuff here, fun stuff here. Okay, so as we were saying here, if I start the game out and I roll a 7 and I roll an 11, I win. If I roll a 2, a 3, a 12, I lose. And I just look at these probabilities. Like this is 6 out of 36. This is 2 out of 36, and so forth and so on. And as I mentioned earlier in the video, basically a third of the time the game will end on this first roll, and you can see 2/3 of that will be wins and 1/3 of that will be losses. And that's just the way the mathematics of the games work. And so that's the easy part of all of this, because that's just a one and out kind of deal. And now you can see now for all the other numbers that we just have to start, this is why I've demarcated this as one roll and this is as, continuation, is that now we have to compute what would happen for 4s and 10s, 5s and 9s, 6s and 8s. And so this looks more complicated. We just have to do 3 math operations on this, because the 4 and the 10 will be the same, the 5 and the 9 will be the same, the 6 and the 8 will be the same, and we'll see what we add up to when we get to the end of this. And so now, as I was saying, the probabilities of everything have to add up. And so, like, if so this would add up to 33%, but everything else has to add up to 100. And right now it will. If I just put the numbers in here for all of these things, it would add up to 100%. But now for the 4s, and I go, okay, 4 is 8.33333%. And I go, I'll just put this in here, and I'm doubling up on everything. But if I did that for everything, I'd get a number that's larger than 100%. And that's just because I've doubled up the numbers for the wins and the losses for all of these things. And so just to finish this up here, just to say, now we have to reduce down each of these individual possibilities, because of this 11%, some of it's going to be a win and some of it's going to be a loss. Oops, 13 points. And I should get 160-something%, right? Or no, wait, what? Oops. I gotta double this up here. I should get 166% or something like that, right? And 55, yeah, 100 and, well, what is the sum of that? Just to be 100% clear. 166%, because I'm doubling up the 67% of everything else that wasn't accounted for in the red zone here. So yes, so far, even though it doesn't look right, I'm getting there. I'm on the right track for everything. And so the house edge is just going to be the number of wins, I'm sorry, the number of losses, because that's the house wins, so E23 minus 22. And right now, if we just played it this way, yeah, I would have an 11% odd, but or 11%. But let's not discuss that. So let's talk about this. So let's roll a 4. If I rolled a 4, the odds are 8.333%, as we discussed here. And so now we've discussed now, as always, is that we have to figure out the resolution to this. And so now, this is where things get slightly trickier. We say, well, all the numbers that aren't x, which is the 4 in this case, and 7 don't matter. So like, so there's a lot of numbers that we roll a 6, and we go, nope, don't care, keep on going, keep on going. However, how many chances are there for me to win? That is the 4, and that says there's 3 possibilities here for me to roll the 4. If we go back to whatever this here, and I said, here it is. It's 1, 3, 2, 2, and 3, 1. Those are the 3 possible ways I can roll a 4. And I go, okay, that's how many ways I can win. How many ways can I lose? And then that's 6 different ways, right? Because there's always going to be 6 ways to roll a 7, and it doesn't matter what the die is. There's 1, 2, 3, 4, 5, 6. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 1, 6. Always that. And so now what do I do here? And they say, like, to win, there's 3 possible ways to win, but then there's 9 total ways to end the game. And so because you just add these up, I say this is the number of wins, this is the number of total possibilities. There's 3 wins out of 9 possibilities. There's 6 losses out of 9 possibilities. So if I take this number, I multiply it by this number, I divide it by this number, and now I will break everything up, and I can copy. I can't 100% copy that. I got to go in here. Oops, E7 it. There we go. So now those are the possibilities, and if I add these 2 up, this number and this number will be the same because I'm taking this probability and I'm breaking it up into 2 separate pieces, and then they better add up to 100% at the end of the day, and they do. So this is how I calculate the total odds of rolling a 4 and winning, rolling a 4 and losing. And so 2.77777 whatever, and 5.5555555, and I can do the same for the 10s. And so that accounts, and things are getting better. This number is going to get down to 100%. It's going to add up to 100% eventually. Let me put these 2 together so we can see that here. So right now it's at 150%. But it will get closer and closer and closer to 100 as we correct the calculations. So let me put the ones in bold, the ones we've done, and let me unbold so we know which ones we have to do to finish up. So now, the 5, it's an 11% possibility, 11.111%. How many different ways can I roll a 5? There's 4 different ways. Okay, so there's 4 different ways to win, 6 different ways to lose. So now you add these up and you go, oh, I have a 4 out of 10 chance. I have a 6 out of 10 chance. And again, this adds up because I did all the math right. 4.444 plus 66666 equals 11. These numbers are the same. I've done my math. At least I think I've done my math right. I'm pretty confident. So I can go 4.44444 for the 5, 6.666666 for this, and then come down and do the same. And now I'm getting even closer. And now I can bold out these guys because I've done the math correctly. And so now all I'm left with are the 6s and the 8s, and this is 13.888888. And I say, well, how many different ways are there to win? 5. 5 ways to win. It's always 6 ways to lose. 5 into 11, 6 into 11, and now this number matches up. And so now 6.313131313131 and 7.57575757, and then repeating 6.31313131 and 7.575757. And lo and behold, what do you see here, right? I've done the math, I figured it all out, and everything adds up to 100%. And so I've accounted for everything. And if I play this game the way the pass line is described, then I will get a win 49.2929% of the time, and I will lose 50.71 or 707070% of the time for a house edge which means if I just keep playing this, the house will win my money over time 1.4% at an edge of 1.4%. And all things considered, that's not too bad when it comes to casino games. So like if you play blackjack, if you're bad at blackjack, that's much the edge is much worse. Roulette, all the other games. I mean, the house edge isn't so bad, and if you play the other bets at the casino, then you can actually have a even better zero edge bet when it comes to the way the bets work at the casino with this game of craps. But I just wanted to say this is how you would, this is basically if I broke down that game into every possible way I can win and lose, like what would be the probability of each of these different occurrences coming up, and they all add up to 100%. And do I want to play this game? Hell yeah, it's a lot of fun at the casino. I just wish I could play with I wish I could play with fake money or other people's money, because it is it's anxiety because you have to usually pay a lot of money to stand at that table, especially on a Friday or Saturday night in the Chicagoland area. So anyway, so this is how you would do the probability for, let's say, the end result here. What I would care about is what is the total house edge of this game, and it's 1.41%. And so if you're in my class and you're watching this because of that, you're going to have to do the don't pass. And so you're going to have to change this up slightly, and you'll have to see how to, and figure out what is the edge for the don't pass. And it's slightly different. It's very close to 1.41%. I don't remember offhand exactly what it is, but if you change things around just enough, you will see that basically it's about 1.4, 1.3%. But it goes the other way around, because remember, in the don't pass, the 12s are eliminated from, they're not a win, they're not a loss, they're a push, and everything else kind of gets reversed. Okay, so that covers what I wanted to cover, the mathematics of craps. As always, if you have any questions, comment below, and I'll get back to you as soon as I can about this video. And at least from my perspective, the spring 2021 term is in full effect now, and so I'll be making videos, all sorts of things, and I hope to see you guys in those videos in most likely your future and my past. So thank you, everybody. Have a great day. Next time.